Well, welcome back here as we are now starting to take a look closely at the periodic table of elements. We're dissecting it, if you will. And we're realizing there's a lot of quantum numbers on this periodic table. The first quantum number is n, called the principal quantum number. It's allowed to be 1 to 7, theoretically infinity. But count how many horizontal rows there were. 1, 2, 3, 4, 5, 6, 7. The principal quantum number is really represented vertically. Or horizontal rows, I should say horizontal rows, 1 to 7 vertically, but each number corresponds to a different row on the periodic table of elements. We learned that the s sublevel is made up of one orbital and it holds 2. There's 2 columns right here. This is the s block of the periodic table of elements. Look at right over here. There are 6 vertical columns right here. The p orbital is made up of 3, or the p sublevel is made up of 3 orbitals, each orbital holding 2 for a total of 6 electrons. This is called the p block. Here we counted 10 vertical columns. The d sublevel is made up of 5 orbitals, each holding 2 for a total of 10. This is the d block. Here in La and Ac, lanthanum and actinium actually are in here. Starting with cerium, thorium, there were 14 vertical columns. The f sublevel is made up of 7 orbitals, each holding 2 for a total of 14. This is the F block. If you look at a periodic table of elements, and this is a little different version of it, but it's kind of the same thing. Here's our 2 vertical columns here. This is called the S block. Here's our 6. This is called the P block. Here's our 10. This is called the D block. And there's the schematic of the bottom of the periodic table. There we had our 14 for the F block. Looking at the quantum numbers, we remembered, hopefully, you remember that the number of electrons that fit on the different levels of the atom can be found by taking the quantum number, squaring it, times 2. Think back to your notes. Where do we get that? If we look back at our notes, how many electrons fit on the different levels? The principal quantum number let you know. The number of orbitals was n squared. The number of electrons that could be held was 2n squared. So we said the first level, 1 squared times 2 is 2. The second level, 2 squared times 2 is 8. The third level, 3 squared times 2 is 18 electrons. 4 squared times 2 was 32 electrons. 2, 8, 8, 18, 32. Holy cow. Are those numbers on the periodic table as well? Let's start looking. First row of the periodic table. This is our first level. We said 1 squared times 2 was 2. Hydrogen and helium. There's your 2. 2 squared times 2 was 8. I'm on the second level. 1, 2, 3, 4, 5, 6, 7, 8. How many did the S hold? 2. How many did the P hold? 6. 3 squared times 2 is 18. 1, 2, 3, 4, 5, 6, 7, 8. Third level. Wait, we're missing 10 on the third level. We're missing 10 on the third level. Here's my first 10. Is this the 3D? Is this the 3D right here? Remember, the third level, if you recall, the third level has an S, a P, and a D. Why would the 3D, look back at this again, why, this has to be the 3D, but why is the 3D being filled after the 4S? 1S, 2S, 3S, 4S. And this is where it's nice to flip back to this dissected table right here. This is the 1S, the 2S, the 3S, the 4S. There's even a better version of this. Looks much like this one right here. But this is the Aufbau order of filling table. This is just the periodic table. We can see all the elements in the squares. But take a look at this for a second. and this is in your notes as well. This is Aufbau's order of filling. Quantum numbers. Here's our S block again. 1s, 2s, 3s. Here's our 2p. There is no 1p. The first level only has the S. Second level has the 2s and the 2p. The third level has the 3s and the 3p. And the 3d. Can you see the 3 right here? That's the 3d right down here. But why would the 3d on the periodic table come after the 4s? That gets us back to Aufbau's order of filling. If you remember, in our notes, we mentioned Aufbau's order of filling. Aufbau's order of filling. Here it is. The lowest energy level, sublevels, get filled first. You start from the bottom and you move up. How do you know the energy of its level, sublevel? You add the first number and the second number. You add the first number and the second number. And the lower totals get filled first. So what is the energy of the 1s? You're like, what are my two numbers I'm adding? We added a 1 and a 0, but where do we get them? The 1 is right there. But you have to remember the S is the letter, that's the shape code for when the second number is 0, the L values. So when our second number is a 0 and our first number is a 1, this would have an energy of 1 plus 0, that's 1. The second level, the S is always 0. 2 plus 0 is 2. This one, the 2p, gets filled after the 2s. Why is that? When you're in the 2p, that p is the code for the quantum number, second quantum number being a 1. 2 plus 1 is 3. 3 is bigger than 2, so the 2p actually has a little bit more energy than the 2s. It gets filled second. On the second level, it gets filled second. The third level, the 3s, is going to be the lowest. 3, when you're in the S, it's a 0. 3 plus 0 is 3. In the 3p, the energy is going to be 4. Once again, when you're in the p, that second number is always a 1. 3 plus 1 is 4. Now we get down to the discrepancy. Why does the 3d get filled after the 4s? Well, the energy of the 4s, 4 plus 0. That second number is a 0 when you're in the S. But what about the 3d? The first number is a 3. But when you're in the D, the second number is a 2. 3 plus 2 is 5. The 3D actually has more energy than the 4s. It's closer, but there's 5 orbitals to fill. That's more energy. The 4p gets filled after the 3d. 4 plus, when you're in the p, the second number is 1. 4 plus 1 is 5. This is a 5, this is a 5. But if you remember, according to Aufbau, ties are broken. The lower n is the tiebreaker. The lower n is the tiebreaker. So the 4p gets filled afterwards. So there's our 3d. 1s, 2s, 3s. 2p, 3p. 4s, 3d, 4p. And then we come down to this part of the table. Things are very interesting right here. Here's the 6s. What's the energy of the 6s? 6, when you're in the S, your second number is a 0. That's a 6. The 5d, what's the energy of the 5d? When you're in the D, you recollect second number was a 2. So we come down here. 5d, 5 plus 2 is 7. But if you look right here, we told you that the 4f is broken off and stuck there just to save horizontal space on the paper. So when we go from 57, what is the energy when we come to 58? This is the 4f. The f does not appear on the periodic table till the 4th level. We remember that from right here. When do we first see the f? 4th level. There's our first f right there, 4f. What's the energy of the 4f? When you're in the F, your second number is a 3. So we replace the F with a 3. 4 plus 3 is 7. 7 is bigger than 6. So we go from 6s to this 7. energy of 7 in the 4F. Then we go back up to the 5D. 72 is right here. So we just follow right back up to 72. There's the 5D. It is also 7. Why does the 4F get filled before the 5D? It's because the tiebreaker, they're both 7s. The tiebreaker's lowest first number. This is a 4. This is a 5. The 6P also adds up to 7. When you're in the P, the second number is a 1. 6 plus 1 is 7, but 6 is bigger than 5. 5 is bigger than the 4, so the order goes 6S, down to the 4F, back up to the 5D, and over to the 6P. So we told you way back when we were doing the orbital notations that you didn't need to remember and memorize the order underneath. It's because the order is on the periodic table of elements. The next question we want to answer are what all these little S1s, S2s, D2s, S2P1s, what are all these little things color-coded on this dissected version of the periodic table, Aufbau's order of filling? What are all of those? In our next video, we'll explain where those come from.